Hello, everyone. My name is Ben Lanir, and this summer I worked with Solaine Zhao under Professor Vandenberghe on optimization techniques for linear dynamic system identification. So our goal this summer was to create a computationally efficient tool to clean and fill in corrupted data. This is important because almost all fields use data, as fields can use data analysis to improve any aspect of their field, and it is very difficult to create an efficient tool that can both clean and interpolate data. So some important things for our project were dynamical systems and convex optimization. Dynamical systems are just system that changes over time based on its current state as well as any forces acting on it. And convex optimization is a technique for finding the best set of values to meet some criteria. In the case of convex optimization, it can be performed efficiently. So the way we did this, we used a package for MATLAB known as CVX, and we used randomly created datasets as well as datasets from online repositories. The first step was to gather our data sets. Then we created an optimization function and input. The optimization function I'll get to in a moment. The input was our gathered data sets with some values removed and some noise created to properly corrupt them. Then we would run our optimization function and we would evaluate the results of the optimization. And finally, we would adjust the penalty weights of our functions accordingly. So adjusting any values that may be in our functions to try to get a more accurate cleaned data. So the mathematical methods. Our actual optimization function was created using this equation shown in blue, the nuclear norm of the Huncle matrix of the input data plus the Frobenius norm of the data multiplied by a mask. So the first part of this function was the nuclear norm of the Huncle matrix. The Huncle matrix is a special type of matrix that takes our input matrix as an input and creates a matrix that can be read left to right, top to bottom, except that it's special because every anti-diagonal contains all the same values. So the position 1, 2 contains the same values as position 2, 1. Then we would try to minimize the rank of this matrix. Minimizing the rank of this matrix would mean our input matrix would be a good linear dynamic system. However, minimizing the rank of the matrix by itself is a very computationally inefficient problem. So instead what we would do is minimize the sum of the singular values of the matrix, as a matrix's rank is equal to its non-zero singular values. And so summing together the singular values, if you achieved a low sum, you would estimate that many of those singular values were equal to 0. The second part was an error term. This is the Frobenius norm multiplied by a mask. This is simply subtracting our estimate at what the clean data is from the original data to ensure that it does not stray too far from the original data. This will be multiplied by a mask because we would not want to include any of the deleted points in this part, as it wouldn't make sense to do that. So our results are shown here in the top left in these 4 graphs. The first 3 graphs represent signals from our clean data. The first one is an input and the second 2 are outputs. The orange represents the original data and the blue represents the clean data, with the green circles and red X's representing the present and missing corrupted data respectively. As you can see, our interpolator did a good job at actually interpolating the data and making it very close to what the original data was. In fact, with 20% of the values removed and 30% noise, our interpolator was able to create 90% data, create data 90% accurate to the original data. Our final plot is the plot of our singular values, which, as you can see, there are roughly 18 large singular values before they quickly go towards 0. Now, these values aren't exactly 0, but that is likely just due to error. And this is a logarithmic scale. So after 18 singular values, they very quickly go to 0. And therefore, it is very likely that our Huncle matrix trick was able to create a low rank matrix and thus a linear dynamic system. So some conclusions from our research. Our experiments with the test data support this mathematical model as a great way of cleaning and interpolating data. And our results have broad impacts on all fields that involve data analysis, which is pretty much all fields, with some examples being the biomedical field, the financial field, the technological field. And some future directions for our research. We would like to employ more complex optimization techniques. This includes the alternating direction method of multipliers, which is a more efficient technique than what we used. We would like to implement our function in Python, as Python is a more widely used language. And we would like to use our function on a more diverse set and more real-world applicable data sets, which include biomedical data to estimate biomedical signals. Thank you.